E. Okay, sorry. I missed only 10 minutes. Okay, good. So that's what we learned last time. And then today, what I'm going to do is to solve example. So people just, if this is the exact solution of the Ising partition function. This is due to Conformal. So that's today's the goal. And yeah, the first goal is this. The strategy is the relation between d plus 1 dimensional classical Ising. Classical I think is to map to the d-dimensional quantizing Ising model. And then we use so-called Jordan-Wigner transformation. To diagonalize. Have it done. Have it done of the quantum method. So that's the strategy to get the Onsager's exact solution. So Onsager's exact solution is a milestone in theoretical physics. It's it's a remarkable result, and from which lots of important result has been derived. So it's very important to learn this. And then Jordan-Wigner transformation is also a very important role in quantum physics. So it's important too. So let's set that. So let's set d equal to 0. So the one-dimensional Ising model. So this is the statistical partition function, and then we just consider some, say, periodic Ising, like this, and with n set, so one-dimensional Ising model. So this Boltzmann weight, so this Boltzmann weight can be taken as the following way. So So e to the k is I. Can be understood like this way? Because I mean Si can take, so this is +1, -1, -1, +1. Okay, if Si, so say this one is Si, and then this is I +1 is equal to this one. Then, so you can have this kind of matrix, 2 by 2 matrix. Okay. So this can be understood as capital S or okay. And so therefore, in this case, the Z of K can be understood trace of S to the N. Okay. So, so now what we did is that it's very similar to Hamiltonian. So this can be compared to trace of E to the whatever Hamiltonian times Hamiltonian times T to the N. Okay. Can be understood as so Hamiltonian is the 2 by 2 matrix. E to the H delta T can be understood as this 2 by 2 matrix. 2 by 2 matrix, and then if you just coming back to here, so this Ising model can be understood as so this is a time direction, and at each side you can have a delta T. How to say time translation by S matrix. And then you can come back to the after n step, you will come back to the original point. So therefore, you have to take a trace. Okay. Take a trace, and take a trace. Take a trace means it's just a 2 by 2 matrix. So therefore, it's a 2-qubit quantum system. It can be understood as 2-qubit. So therefore, here. So at this moment, you can translate everything in terms of the Hamiltonian or 2-qubit system. So this can be understood 2-qubit system. So partition function of the 2-qubit system of the so this is quantum. So this is what I meant is the one-dimensional classical Ising to zero-dimensional quantum Ising. So this can be understood as a zero-dimensional quantum Ising. So to get this partition function, what you need to do is to evaluate trace of S to the N, which is very easy. Just diagonalize this matrix. Okay. And if you diagonalize it, this one can be understood as E to the K. Like this one. Okay, so you can diagonalize. So it's just symmetric matrix, so you can have a eigenvalue. Eigenvalue is this one and this one. So therefore, what you need to do is okay. So this is the Hamiltonian, which is equal to like this. Okay, so that's the partition function. Okay, got it. So what's important is that this classical, I think, what's important is that if you just mount to the quantum Ising case, you just diagonalize this matrix. That's the only thing we should do. And then diagonalize 2 by 2 matrix super easy, so that you can just have this. Okay, and then and the free energy is the free energy this one. So free energy is as I obtain n log cosh, okay, times log of 1 plus dash n to the k. So that's it. So let's move the two-dimensional class Ising. So you have two-dimensional class Ising is also similar. So you have a, how to say, one-dimensional Ising, whatever. And then the other is also one-dimensional Ising. And somehow they interact each other. So at each, how to say, one-dimensional Ising, one can use this method. One can use this method to obtain the Hamiltonian. So to rewrite this Hamiltonian is two Hamiltonian or 2 by 2 matrix with the following thing: e to the k prime sigma x. Sigma x is the Pauli matrix. So the sinh k prime cos k prime like this way. And if you use this relation, whichever. If you use this relation, this can be understood as the following. This can be understood as the so S can be written as 2 times sinh 2k. And e to the k prime sigma. Like this. So, if you use this relation, one can easily derive that this matrix can be written in terms of this. Okay. And then, so that is the Hamiltonian for it depends. But the Hamiltonian of each vertical direction, S is a vertical direction, so each vertical direction. Okay, like this. However, in two-dimensional case, there is a interaction between two adjacent sides to the horizontal direction. Okay, so adjacent horizontal direction is also you need to consider that the interaction in the horizontal direction. So therefore, so what you need to do is that the partition function can be written as follows. So the z k and k prime trace e to the k sum of the sigma I plus 1 z. So this is z, and the plus k prime sigma I. Like this. Okay. And to that. Fine. So what we are doing, so S is the horizontal direction, horizontal Hamiltonian, and then that is you have to take some of, say, this is the n side. In total, this is the n side. There is a capital M side here, capital M side. Hopefully it's okay. Yes. Okay, and then so you take the S is the vertical direction to the n side, and then so this is the s part. This part is the s, and this will give rise to s. And then here, this is the vertical horizontal interaction. Interaction. That will give you the quantum one-dimensional quantum Ising model, and that will give you the, so in total will give you the Hamiltonian quantum Ising model, and then what we need to do is that you have to consider the one-dimensional Ising model between a quantum Ising model in this horizontal direction. That's what we need to do. So Hamiltonian of the quantum of one-dimensional Ising model is as follows. Okay, so at each how to say, the vertical direction, you get 2 qubit. Say 2 qubit is something like I don't. It's schematically, let's say, right? I don't know, 2 qubits. So schematically, just write down like this way. Schematically, 2 qubit. Whatever, like this. So that's the we consider, and you have to consider some product of these 2 qubit states. Hamiltonian of the one-dimensional Ising is given by the follows. It's just KB, T, K. Like this way. Okay, so this is a Hamiltonian quantum model. Quantum spin chain with C. So therefore, this can be understood as some kind of like a quantum spin chain with the this guy is the external magnetic field in the x-axis. So this is the quantum spin chain because it's a power matrix in adjacent side, and this can be understood the x direction, x-axis external magnetic field. In x-axis. Okay. It's fine. Okay, so to understand this Hamiltonian, what we are going to do is as follows. So we introduce one can understand the Kramer's one by introduce some disorder operator. So mu. I n, so sigma I x, and mu n. So if all the states are spin up, all the states are spin quantum Q2 qubit is spin up. So mu A of Z that acts on like this way. All are spin up states. Spin up states. Then this will give you the follows. The first, so sigma I is just sigma x is something like 1, 1, 0, 0. So this is the sigma extra. Is it okay? Okay. See. So therefore, if you ask the spin up state, it's just lower. So and it just starts with minus n over 2 to a. So therefore, okay. So that's what's going to happen. So this is the A state. So minus n over 2 to a plus 1, and then here you have the n over 2. Okay. So that's the, so therefore this is, so mu A of Z will create a disorder here, disorder at the side A, okay, at the side A. That's why it's called disorder operator. Okay, so you can understand this kind of like a solid located at the dual side edge. Okay, and moreover, Hamiltonian upstairs can be written as follows by using the mu. One can write down, rewrite this one as follows. Okay. Adjusted. So this guy is the mu AX, newly defined mu AX is replaced this part, and the sigma IX can be just take the product between adjacent side. Because then we know that the sigma X, the product is equal to 1. Square is equal to 1. So therefore, if you have an adjacent mu A and mu A plus 1, if you multiply it together, what's left is only the sigma IX at the position A plus 1. Okay. Do you understand what I mean? Is it okay? So sigma over 1x, 2x, and x, and and 1. So if you multiply this will give you 1, 1, 1, and what's left is this. And so. Okay, so that's the case. So this is literally the Kramer's one duality at the level of quantum. So this is KW duality. Kramer's one duality at the level of quantum Hamiltonian. It just exchange K and X, K prime, which exactly what we saw in the previous time. Okay. Any questions or comments? So in the case of low temperature is the T less than Tc, which means the K. In this case, the sigma will take expectation value, and the disorder operator is the 0. On the other hand, so this is low energy, low temperature, high temperature. Like this. So on the low temperatures, spin is the try to align them together. Therefore, spin operator will take the documentation value. On the other hand, for high temperature, this disordered operator will take the documentation value. That can be easily seen because the mu and the sigma will swap the role under the Kramer's parameter. Okay. And so that's why it's called disordered operator, because I mean, at high temperature, it's more like a spin, try to, how to say, is the kind of random. So therefore, if the disorder operator takes the documentation value, then this means that it's really disordered. The state is really disordered. Okay? That's what's really happening. Fine. Any question at this moment? So now we want to diagonalize this one. So next, what we need to do is diagonalize this Hamiltonian. This Hamiltonian. So that's the next task. To do that, we will do some trick. So it's called Jordan-Wigner transformation. So to do that, we introduce the Fermat operator. With psi I, like this way. Like this one. Pairing off psi I is satisfied by Conformal algebra. 2 times delta ij. So this satisfies Conformal algebra. So this one can be just achieved by introducing the following way: 2k minus 1. Like this way. Like this way. Okay. So then you can just easily check that this condition is satisfied. This one is very easy by using the Pauli matrix algebra. I mean, so x this one you can easily check by using Pauli matrix. So that means it's a local computation. So here everything is the same. So it becomes 1, and then local computation is what's important is the case point, and you can easily check that this is the case. Okay, so that's that you can easily check by computational relation. Fine. And then what's important is that if you introduce this Fermat operator, one can just obtain the following. So, and also, okay, so that's very easy to consider as coming from here. You can easily see from this point, from here. So, if you have the 2k and 2k minus 1 product, what's left is that the so you just multiply these two to get the sigma kz, and then if you just have a sigma k y and a sigma k plus y, then sorry, so 2k and 2k plus y. What's important is that the so sigma z, sigma x will give you sigma y. So that's the what's really happening here. Okay. So, I think so. Yeah, that's one. We'll keep this one. Now for you get this one. You get this one. So now you can compare with this Hamiltonian. Okay. So now, I mean, if you switch the x goes to y, sorry, z goes to y, and y goes to x, and x goes to z. So you just do the permutation. Then this Hamiltonian can be written IKB Hamiltonian can be written like this way. So this part will replace this one, and then this part will replace this one. Okay. So and we call periodic foundation. Periodic boundary condition means that to n. Okay, so that's the case. So this Hamiltonian can be written as follows: minus IKB psi transform psi, where m psi, where psi is the psi1 dot psi n to n. This is n, and m can be written as follows: 0k prime minus k prime. 0k and k, 0 and k prime minus k prime, and then this 2n by 2n matrix, 2n matrix. And the important thing is that at the end you have this kind of thing, k will show up like this. Okay. So this kind of matrix will show up. Okay, so that's the Hamiltonian. So starting from this quantum Hamiltonian, introducing this parametric operator, which is just a product of this bunch of product of this power matrix. Since power matrix written here. Okay. And then, so the Hamiltonian can be written in terms of 2n by 2n matrix times this conjugate by sandwich by psi. Okay, so that's what's really happening. I mean, you can do that local computation, for instance. I mean, if you look at here, so it has k prime, psi 1, psi 2, right? And psi 3, psi 4, right? Like this way. And here you have k, psi 2, psi 3, plus, what was that? Psi 4, psi 5, and so on. Like this way, like this way. So psi 1, psi 2 is really coming from here. Okay? And then coming here. And psi 2, psi 3 is coming from here. Okay? And then if you divide it by 2, it's okay. And then psi will satisfy this threefold algebra here. So therefore, you have the minus sign. You have a minus sign in the opposite. So it's an anti-symmetry matrix. And then, so therefore, Hamiltonian is there something wrong? So the Hamiltonian, so diagonalization Hamiltonian is diagonalize this matrix, 2n by 2n matrix. Okay. It's very simple. It becomes very simple. Okay. Okay. And to diagonalize Hamiltonian, so this change is called Jordan-Wigner transformation. Okay. So this change is called Jordan-Wigner transformation. Fine. Okay, and then what's really happening is that so we try to diagonalize this 2n by 2n matrix, which is I mean, this is how we should learn Fourier transformation. I mean, Fourier transformation is literally to diagonalize this Hamiltonian. What we need to do is that we just consider the vector. So omega is the 2nth root of unity, nth root of unity, nth root of unity, and then b so like this way. So essentially you have only two entries, A and B, and then just multiply the nth root of unity, like this way. So then you can span the 2n column vector. Then you multiply this matrix n, acts on it. Then, so what's really happening is that so if MP also can be written as follows. Minus R and B can be written as follows. Omega minus A tilde, omega inverse B tilde, A tilde, B tilde, and so on. Okay, so then trying to find eigenvalue is essentially that to solve this equation, to solve this 2 by 2 matrix problem. So this is just simple calculation. what you really need to do is really, if you multiply, so it's a very good exercise to do. So this multiply by b, so b is something like this one. A, B, and then omega inverse B, omega inverse B, and omega A, omega B, and so on. You just multiply, and then try to compare how does the vector look. And what's really happening is that as you can easily see from here, for instance, if K prime is hits A, okay, if you multiply K prime hits A, minus K is hits omega inverse B. So that will give you this one. Sorry. Omega inverse A, sorry. Okay. That will give you, so omega inverse of A, and omega, if A hits K prime, omega inverse of A hits minus K. Okay. So that should be something strange. Okay, so it's opposite, sorry. So yeah, so if B hits K prime, so omega inverse B hits minus K, so therefore that will give you this guy. On the other hand, if A hits this guy, omega A hits this guy, acts on this one, that will give you this guy. That will give you this guy. This guy. Okay? And if you compare with this column vector, and this is locally. If you solve locally this one, you can diagonalize this matrix. Okay. This is how you perform the Fourier transformation. Fourier transformation. Fourier transformation, literally, you just diagonalize this matrix. Okay. And then solving this, the eigenvalue is super easy. So eigenvalue is the as follows. So the solving this one is so this is the case. So these are eigenvalues. I mean, it's easy to solve this 2 by 2 matrix like this way, 2 by 2 matrix. So these are eigenvalues. And since S runs from 1 to n, and there's a plus minus and absolute value. So therefore 2n eigenvalue. Okay. These are eigenvalue of this one. Now we could solve. We already solved this quantumizing one. So it's a very nice way, but it's a very, very like a miraculous way to find the Hamiltonian of the Ising model. I mean, so the partition function is usually, statistical partition function has to solve all possible configurations of the variable sum of sigma I, sigma j. So you have to sum up all possible configuration or Hamiltonian minus beta h, whatever. So all state. So this is usually very difficult. Okay. But in the case of quantum, so Ising model, two-dimensional Ising model, one can perform the first map from 2D classicizing to 1D quantumizing, and using Jordan transformation, one can diagonalize matrix Hamilton. Okay, so now for like this way. So this one is equal to n. Like this. Okay, so it's very simple. It's miraculous. And the free energy of this system is just taking log of this one. Free energy is the 1 over n log k prime, and then equal to log 2 plus 1 over n sum over like this, the free energy, like this. So it's a very remarkable result, and it's a very remarkable result because of the, I mean, you can sum over all possible. So this is essentially what we're doing, the sum over all possible states with the Boltzmann weight, but somehow in the Ising model you can do it. And take n goes to infinity. That's n goes to infinity. One can just take this is log cosh k prime k e to the minus 2 pi r s divided by n. Oh, sorry, there is no s. So this becomes L, L. And dl over 2 pi. 2 pi. dl over 2 pi. So that's the so instead of this summation is this is s is equal to 1 to n. Once you take n to infinity, this becomes continuous variable, and the sum becomes integral. That's what's really happening. And moreover, the spectrum MS will become something like a. So did I write? Oh, I already wrote. Sorry. MS used to be something like this one. Like this way, and then this one can be just written down as follows. K minus, so MS can be written as like this. Okay, like this. Therefore, this can be written is the k minus k prime. Okay. And as you can easily see, so this is bounded by some positive number. Bounded for when k is and k prime are different. Okay. Bounded So the spectrum, so the energy spectrum is somehow discrete. So you can have E here, you have a discrete spectrum when K and K prime is different. On the other hand, so at the critical temperature, when K is equal to K prime, this will become like this way. And then once you take n goes to infinity, it becomes gapless. It becomes gapless. This means that. So therefore, so when K is equal to K prime, which is the critical temperature case, then if you consider lots of side, then the energy spectrum is clearly it's really continuous. It becomes like this. Energy spectrum will become like this. So there is no gap between first ground state or first excited state, second excited state, and so on. So that this means that this clearly suggests that this is the CFT description. CFT. So at the conformal point, at the critical point, so therefore there is no gap between. So energy spectrum is not bounded by any positive numbers, and the spectrum becomes. So this means if it is bounded, this means that there is some scale in the field theory, in the system, in the physical system. Okay, so then they become gapless. Like this. Any question at this moment? So this is the one way of deriving the on-cycle result. Another way is the I don't know. I mean, there are lots of ways to derive this on-cycle result. It's a very nice one. So another way to derive the on-cycle result is that there are lots of ways. Another way is just introducing some disorder operator and so on, and then consider make it graph and so on. I mean, which can be maybe homework or can be derived in next time or so. I'll think about it. But this time, so let's stop here. So now let's consider some property in Ising model. Property in this model. Ising model. Okay. Property of Ising model. Let's consider sigma x2 in the high temperature region. High temperature region. So this one can be understood as the 2 times cosh. Okay. Like this one, where P is at the so if you consider the Ising model. So sigma x1 is here, and sigma x2 is here. Sigma x2 is here, and then path is this p is the any path between these two. Because now we insert the operator in here, x1 and x2. So therefore, once you do the statistical partition function, so you have to start with this, the path has to start with the sigma x1. Okay. Otherwise, I mean, you have to do the same thing, same as before. So the cosh k plus sigma I, sigma j. Like this. If you use this relation, I mean, this sigma x1 should cancel with this sigma x1. Otherwise, when you sum over all possible states, so I mean, they cancel. They will give you a trivial contribution. So the path should start with sigma x1, and it should end on sigma x2. And you consider all possible paths in between these two. Okay, so that's the correlation function at the high temperature. The function can be obtained. On the other hand, how about disorder operator? So we already introduced disorder operator. So mu x1, mu x2, start. Let's go start. I call it start because I mean you have to take a dual side. To take the dual side in low temperature regime, low temperature regime, and then, so if you take a dual side, like this way, dual side, and then you put the mu of x1 star in here, and the mu of x2 star in here. So star means the what was that? The dual side, position in the dual side. Okay. Okay. So then what we are doing is that you just sum over all possible. So this one is the sum over possible states and the product of adjacent I and j, and then e to the k sigma I sigma j. So that's the usual way of doing the partition function. But in this case, PD. So plus or minus. Okay, plus or minus. So you swap this Boltzmann weight. So Boltzmann weight by sign for potentially PD. So this plus minus choice of plus minus sign is that if you have this path is the connected is the PD. PD like this way. Then so this yellow line, on the yellow line, so you have to take a minus sign. On the other adjacent red line, you have to, as usual, pick a plus sign. That will give you the correlation function, 2-point correlation function, disorder operator. Okay. And the sigma I, sigma j is of course the spin variable, plus minus. And this one is not the PD actually. So this differential looks like the depends on choice of PD. Okay, but as you can easily see, so it's independent because I mean, if you just consider this kind of path, okay, like this way, if you consider the other path, let's see, PD prime, PD prime. So you can easily see that the mu x1 star and mu x2 star like this way. Because I mean, once you have the cross path, I mean, if you just swap the all possible, how to say? If you swap the all possible, what was that? The spin configuration inside, it's equivalent to the going back to the other path. If you consider, okay, let's consider. So Boltzmann weight does not change, and if you just consider this cross path PD times PD prime star cross path, and inside of configuration, if you have swapped all possible spin, Boltzmann weight does not change because I mean minus times minus is equal to plus 1. So therefore, it's independent of choice of the path. So this definition looks like it depends on this path, dual spin change, dual lattice, but the correlation function itself is independent of the choice of a path. Is it okay? This point. Do you understand? This point. So this is the case. However, if you insert the two kind of operator, sigma xn, spin operator and disorder operator, like this, if you try to compute this one, okay, then this one is depends on the choice of P. So this is sum over sigma x1 equal to sigma xn product Ising plus minus k sigma 1 sigma j sigma I sigma j, where ij adjacent and possible sigma. Also sigma. And of course, this minus sign here is only when this the two adjacent sides intersect with this path. Okay, two adjacent sides intersect with path. Okay, so maybe I have to influence. I have to emphasize this one. I think people do not understand. So I think people losing. I don't know. So here. Suppose you have a plus and minus. Suppose plus minus. Okay? Here, Boltzmann weight, it should be e to the k, and then plus minus. Usually, so if you do the plus minus, this should be minus sign. Usually this plus times minus is minus. So therefore, this is the case. However, since this is the green, so actually this green, if you have a intersect with green line, it should be changed to plus k. Okay, so because we pick minus sign here. Okay, so here, okay, maybe it's better to set the like this way, maybe. set like this way. So in this from here, the Boltzmann weight is K. However, since there's a green line in between, the Boltzmann weight from here is E to the minus K. Okay, so that's the rule. Okay. Is it okay? Do you understand? So that's the rule of this correlation function, this order operator. And this looks like depends on the path PD. Path in dual lattice. However, this is not the case because if you consider this kind of the cross path, suppose you have minus plus or whatever. So configuration, if you go like this way. You can just take like this way. You can just swap to the opposite case. So minus to plus, plus to minus, and minus and plus. Then this statistical partition function do not change. Okay. Here if you change to here minus sign, if you change to minus sign, so it becomes plus sign. So therefore, anyway, so it becomes previous cases. It's a previous case. So therefore, if you have a cross path, you just simultaneously swap all the spin configuration in here. The statistical partition function is the same as before. Same as before. So therefore, which means it's independent path, PD. On the other hand, if you look at this one, the things are different. Things are different. So let's suppose this is, so I immediately write down dual path. Okay, and this is the x1, and then here mu x2. And suppose PD is something like this one. This is the PD, and it's a PD prime. And then you have something like a sigma x1 here, sigma x2 here, like this way. Okay, sigma x2 here, and so on. Then so here, so this sigma is you cannot swap. So therefore, this one is plus minus is number of sigma xi times sigma x1. Like this. Okay. So here minus. So sigma 3 can be something like here, and sigma 4 can be something like here. But anyway, so depends also on this the P prime. So here, if you look at the spin configuration inside here, if you swap the entire configuration inside this is cross path, so these are affected. So the inside the spin operator will be affected. So therefore, these are also inside here is swapped. Okay. So therefore, we receive sign here. So therefore, the difference between PD and the PD prime is really depends on the number of the spin operator inside this cross group. Okay. the relative sign is that they are different. So therefore, this means that the sigma and mu are depends on, so this correlation function depends on global structure of configuration. So this means that where you draw PD and where you put the sigma really affect the value of correlation function. Okay. So therefore, the global structure means the configuration where you draw this path really determines the correlation function. And then, so therefore, they are actually mutually non-local. Mutually non-local. So this is called mutually, sigma and mu are mutually non-local. Mutually non-local. So this is the so mutually non-local means that if you have some mu operator here, and you have a branch cut, and then you just rotate sigma sigma like this way, you will receive sign. If you just pass across the branch cut, you have a minus sigma. Minus. So therefore, it's really like depends on the structure. Mu and sigma depends on the configuration each other. So this is the very important aspect of this Kramer's binary. Sigma and mu are the both sigma is the elementary field operator in the in one side. Mu become elementary operator in the other side, a high temperature regime. Whereas sigma is the low temperature regime, and then somehow they somehow depends on the global structure of the position of each other. And then, yeah, this can be this one can be understood as follows. Like this. So if you just rotate them together, you just get the negative sign. So this is a mutual normal. Okay, let's take a break. I think this is a good place to take a rest. And if you have a question, just tell me. Yes?
What's the relationship between site and equal site?
That's a relay. What's a relationship? I mean, site is the site is each site you have a spin plus minus. You put the plus minus each or spin up and down, whatever you call it. And then dual site is the so you just take the boundary between them. This is a dual site, dual lattice.
What about x1 and x1 star?
So x1 star is the position at the dual lattice.
Yeah. So the relationship between each and x1.
Could you repeat again?
What's the relationship between x1 star and x1?
I mean, x1 is the position in the lattice,
Yeah.
and the x1 star is the position in dual lattice.
Why we call it x1?
I mean, you can call it something different. You can call it this is whatever. Yeah. Alpha, beta. That's also okay. That's also okay. That's also okay. It's just name. Any other questions? Okay, then let's take a break. Yes.
What's the range? We need to consolidate all of the.
Yeah, all the
Not just along the path.
no along the path.
Okay. So when this one we have to.
Yeah.
And
Yes.
okay.
Yeah. 哎呦。Okay, so shall we resume? Okay. So in fact, so if you consider so in fact, if you consider the OPE of the sigma. So we look at the sigma and mu and mutually non-local. So and if we consider the R, so this is a bit ad hoc, but if you can just obtain the computations become like this way. C to the 1/2 psi 0. Like this way. And where psi is the Fermi. It's a Fermi. Free Fermi. Free Fermi. So in fact, the free Fermi and then Ising CFT somehow the continuous limit actually. Continuum limit related to the free Fermi, in fact. And if you look at the central charge of this Ising central charge of minimum order when p equals to 3, it's 1/2, which is the same as the free Fermi. Which is the same as free Fermi. The formula for central charge formula for central charge is C is equal to 1 plus like this way, and then here minus 1. When p equals to 3, you have a 1/2. Like this. Okay, and in fact, so the dimension. So here you have the dimension. So okay, let's recap the minimum model. Well, what are the minimum model? And so here, so you just look at the Beerthorpe representation. You have a phi RS. So there's a primer field here. Such that if you look at the descent compound family, that will contain that will hit the contain compound. Its compound family. Compound family contains singular vector, and then or new state, both new state. So dimension. So if you start to phi RS, so phi RS or HRS, then you just act many Beerthorpe operator. Eventually, at the level, at the RS level. RS, you will get some null state, okay? Null state or singular vector, and from there, so there's a compound family. From here, you have the singular vector will create a lot of null state that will give you subrepresentation of Beerthorpe algebra. So you have to throw away those representation to get the reduced representation. So that's what we learned last time. And in particular, so this phi RS. So this is S, R, I have a lattice. So just recap what we learned. So like this way. So if you just, so when p equals 3, this Taylor. So as you recall, alpha plus E1, what's that? P plus P prime alpha minus is equal to 0. So this is the Taylor is something like that. As far as I remember, tangent Taylor is something like alpha plus divided by alpha minus. Something like this way. And if this is it hits the point on lattice, so this part will cross the OP. So the primary will cross the OP. Okay? So that will give you minimum one. Okay. And in the case of Ising case, we have the 0 on 16 on half. Like this one. Like this one. Okay, and this is the both the homomorphic and anti-homomorphic sectors. Like this. And in fact, the psi of these, so this free primary arises as phi 21 of T and then phi 11 of T. So this is a vacuum. And psi bar up here as phi 21 is this guy. Phi 11 of T cross phi 21 of T bar. Sorry, T bar. T bar. Okay. T bar. And then and phi 21 C and both homomorphic and anti-homomorphic to one case. This will give you this psi bar. Psi bar. And this is an energy. This is the energy tensor operator. In the case of and then let me continue here, and then sigma or mu CC bar is the phi 12 C. So this is 16 1 over 16, like this. Okay, so those are operator, and then OP is can be understood as like this way, and then so this is the OP, rough form of OP, and if you write down a more precise OP, it's going to be a bit complicated. Maybe I should write it down, but. Wait. So, yeah. For instance, if you write down sigma C bar and sigma W bar, and this OPE is something like this one. The leading term is as we know, it should be 1 over 4. And then you have a C sigma epsilon. Three over 4 and the epsilon W. So these are OPE of sigma. So that's the rough form of this sigma plus sigma, 1 plus epsilon. So important thing, OPEs are closed. And the 1 and the epsilon and sigma. Okay, that's the important thing. And then, and of course, the epsilon of C and C bar, epsilon W bar should be 1 over. So what's the power here? What's the power? 2, good. 2. So 4 times 1/2. 4 times 1/2 is. This is a critical exponent. And so on. Okay. So that's the OP of the Ising model. Okay, so that's the case. So therefore, if you use this OP relation, one can find the phi. For instance, if you look at this one, if you take the psi, and then psi and sigma, what you get is that the psi of t sigma and so on. One can have this kind of expansion. So here, at least we use this kind of relation. This kind of relation. Here essentially this is a homomorphic phi to 1, and this one is essentially phi 1 to z plus phi 2 z, phi 1 to z bar. And once the fermion acts on sigma, that will just transform to this order operator, and so on. That's the rule for this OP in this Ising model. And then these are the 2-point function that appear in the minimum model, Ising CFT. And these are critical. So this power is critical exponent. So that's one of the instances of the minimum model. And then we'll take a look at some other example from now. Okay. Any question at this moment in the OP and so on of the Ising model? Fine. So the other thing, so other minimum models, I just explained that. So when P and P prime are related to the like a P and P plus 1, as I mentioned, this is a unitary. Otherwise, the non-unitary. And when P prime and P is say 2, 5, then central charge is C is equal to minus 22 over 5. Okay? So this is called Virasor Lie non-unitary. So non-unitary. So non-unitary means that it has a negative null state. Null state. Okay. And in particular, so this has a conformal weight. So the H is 0 and minus. H is minus 1, the 1/2. So therefore this is the negative conformal dimension. So this is the 5 on 1, and this is the 5 on 2. I want to. It's a negative conformal dimension. So it's not the physical theory. But if you consider some Ising model or statistical model on lattice, and then J sigma I sigma J I and J a minus B sum over sigma I like this way. Then and if you consider B is that how to say the purely imaginary. If you consider purely imaginary. It's believed to describe be described by this minimum model, and this minimum model is the again linear model. Linear model, and this is a non-unitary model. And then, so the other minimum model describes some statistical model. Is it okay? Some statistical model. So for instance, when P is equal to 4, so that is the 4-5 minimum model. So this corresponding to this so-called critical the Ising. So tricritical Ising model is some variant Ising model, and then you need to include some vacancy site. And then, so the Hamiltonian is given by minus J sum over sigma I, sigma J, Ti, Tj, 1 to n, sigma I, Ti, minus mu, sum of n, Ti, I is equal to 1. So like this way. And then, so this T is the called vacancy variable. So it takes 0 or 1. So so the previous case, we consider the case that the each side you have a spin up and down. But in tricritical Ising model, you can have the vacancy. Its side can be nothing. No side can be in this. So at each side there is no spin. That can be possible. That's tricritical. And that corresponds P equal to 4 case. And then I'm not gonna. And the central charge can be computed as follows: 1 minus 6 over P plus 1, and this is the seven over 10. Like this way. And then interesting thing is that there is something very important thing happened. I mean, this kind of stuff is studied by like Cardi and so on. And then important thing is that so if you have the 1, 2, 3, 1, 2, 3, 4, you have a G and T, E, 1, sigma prime, sigma, and so on. And sigma, and so 1 epsilon Tg. So as I mentioned, there is symmetry in the primary field. And the important thing is this is spin. This guy is spin 3½ operator, 3½ operator. And then So sigma and T and epsilon are as before. The spin operator, energy density operator, T is vacancy operator, and so on. And then G is very important. G is so-called G of Z is called supercurrent. So it turns out that this fermionic operator such that this has the following expansion. Sum of G C half R is depends on its fermionic. So you can have either Nebius-Schwarz or Ramond. Like this way. And this will satisfy the so-called n equal to 1 superconformal algebra. I really forgot how to count. Sorry, I don't have confidence. I don't remember. Something like this one. Something like this one. As far as I recall. Maybe not. Maybe I don't think there is such a. I don't think such a thing happens. Some constant, some number, yeah, some number, and so essentially, you know, L is the Hamiltonian or whatever. So if it is L, if you look at the zeros part, it becomes Z. Like this way. Okay. So therefore, G0 is some kind of square root of this L0. Okay. So therefore, so this is called you might have heard of it, supersymmetric charges. So it's a supersymmetric. So therefore, this one has some enhanced symmetry. So n equal to 1 super conformal field. Somehow, if you consider this tri-critical Ising model, you encounter so-called supersymmetry. Okay, so that's the remarkable thing. It was found in the mid-80s. And also, many interesting things happen. So P equal to 5 is called a tri-critical model. So P equal to 5. So this is P equal to 5. P equal to 4. Unitary minimal model. This is and P equal to 5 is called 3-state. Okay. Share over 2. Okay, and like this. So, and sigma and sigma bar can take the omega cube is equal to 1. So this is root of unity. Third root of unity. It's not spin up and spin down, plus or minus. It's e to the 2 by I over 3. So sigma times k. We take this kind of value. Okay. And then that corresponds to P equal to 5 case. P equal to 5 case. Yes. And this has Z3 symmetry and so on. And the important thing is that this one, okay, maybe I think I should write down. So quite magical. If you study this kind of, like a minimal model, you will see enhanced symmetry. So the first instance you encounter is this p equal to 4 case. This becomes super birasol. It's called, yes, including G is called super birasol algebra. And super birasol algebra. And then p equal to 5 case. If you look at the spectrum, 5, 4, 3, 2, 1, 1, 2, 3, 4. There is an operator is something like this one, 0, 3, and then something like this. Like this. So this is the component dimension 3, and this operator WZ has the following thing. Let's see. What was it? Wn and Z n plus 3, and is bosonic operator like this. And then this is called. So this was found by Zamolodchikov again. I mean, Zamolodchikov and Kali are amazing. I mean, wait. So one thing I can tell you that the in 2D CFT, I mean, important person is one of the important person is Zamolodchikov and Kali. And then Zamolodchikov find this W. It's called W generator, and this will form W3 algebra. It's extension. So you have Wn, Wm, and some W, and then WL is some L as far as I remember, and the birasol algebra. I don't remember the detail. Ln plus m plus C over 12 n, and it's square minus 1 delta n plus m c. Here it's much more complicated. Like this way. So this is called W3 algebra. And then this can be generalized to Wn algebra. Okay, Wn algebra. And that is a pretty important role in conformal field theory and many places. Many places. I don't remember the algebra, unfortunately. I should have actually. I should. Yeah, even this one I don't remember. Precise algebra. Can you cheat one? What's the number here? 2? Okay. 2. Okay. And here I don't remember. You can search W3 algebra in your website. Maybe I can do it now. Anyway, so if you ask DeepSeek and someone immediately write down the unfortunately I cannot find immediately. Anyway, let's not. Anyway, so this kind of like a extension. So birasol operator T of Z is a spin 2. This is spin 3, and then for higher spin will appear in Wn algebra. Okay. So this is enhanced symmetry. So you start with the representation of birasol algebra, but somehow you end up with some much richer algebra in minimal model. If you study the even unitary minimal model, that's the interesting thing you will encounter for the study of minimal model. So Later, so this one has the known to have a Z3 symmetry and so on. Okay, Z3 symmetry. Okay, so later we will see the following Lana's model. So you consider later we consider the following model. Action is Lana's move is something like a d squared z del phi bar. I think del phi. Okay, plus there's some potential. So this is some potential. It's not free field, Lana's model. And this will, if you have all the phi to the n, that will flow by it's called renormalization group to some minimum model. I don't remember the p related to n. P is related to n. I don't remember precisely. Later, and this has some. This potential has something called zk symmetry. If it has a zk symmetry, there is a corresponding central charge is given by like this way. Like this way. So from there, so if you solve this one, 1 minus 6 over p and p plus 1, then you can understand the relation between k and p. Okay. This kind of model has been studied by long time ago. Many people. It's called RSOS model. RSOS model. SOS model. And also Ashkin-Taylor model. This Ashkin-Taylor model is one of the RSOS models. Anyway, so if you consider this kind of arbitrary unitary P model, there is some model statistical model one can construct to this to that corresponding to minimum model. Okay, but I'm not going to go into the detail. Any question at this moment? If not, I'm moving on to Conformal block. So I think it's a good place to take a look at the Conformal block. Fine. Okay, so those are example minimum model. So now we consider some more Conformal block. Conformal block. So 4-point function. Correlation function. And then Conformal block. In 2D case. Okay, so we just consider that phi p lambda. So we can just consider. So the last time we consider is the this phi lambda of p and c l minus. Where did I? Yeah, I think it's a homomorphic part. Okay, so minus L1 phi of P of Z. So this is a caloric field, and this is descendant. Okay, so that's the descendant and caloric field. And then sweep-on function, if you consider sweep-on function of this one, phi p minus lambda of z, and phi 1 and z1, phi 2, z2, this here, can be obtained by just some differential operator acts on the, or more precisely, this is the my notation. My notation is this one is L minus lambda. L minus lambda acts on phi p of z. Like this. Okay, so and then this one can be understood as the differential operator. And the most singular term in a quotient is as follows. So singular term appear as follows. C1 to P lambda is some C1 to P C1 to P and then beta 1 to P lambda, and then anti-homomorphic part is important. Okay, like this. If it is the okay, if you consider homomorphic part, it becomes like this. And this one is complete by determined by representation of the algebra. Okay. Okay, and then so this will determine Beer's algebra, which I will explain from now. And yes, so and then 4-point function, if you consider phi 1, t1, phi 2, I only consider homomorphic part. Phi 4, c4. If you consider like this, one can fix the bisyllable conformal transformation. Z1 is equal to 0, Z2 is equal to 1, and Z4 is equal to infinity. One can fix like this way. I think that's not what I said. Z1 is infinity. Okay. Z4 is 0, and Z3 is fixed. Z3 is fixed. It cannot be fixed. sorry, C3 cannot be fixed, and this is called cross ratio. Cross ratio of this 4-point function. Okay? And cross ratio is equal to this. And then we can just write down the G 2, 1, 3, 4. Like this way, and this can be written as follows: sum of C1 to P and C3 for P, and then you have a so-called 2, 1, 3, 4, and P and X. So this is a rough form of the conformal block. So it's a 4-point function. Precisely speaking, yeah, this is only goes the holomorphic part, and then this is sum over P. Okay, so sum over P, and then I will explain what this means. 4-point function. Is that the so you have a phi 1 of infinity, phi 2 of 1, phi 4 of 0, and phi p lambda, like this. So like this way, and from here one will get the structure constant 1 to P. From here, one will get the C3 for P. Okay, so that's what you get. And this structure constant is, of course, the one that appears in 3-point function. Is the C1, 2, 3, C1, 2, and some power. C2, 3, C4, 1. Like this. And some power. I'm not going to write that. And this is structure constant. And that appears in the only like we appear here. And what's important is this guy. And this one is called conformal, and which I'm going to determine from now. Okay. And this conformal block can be written as follows. Okay, so that's the conformal block we consider. Oh, so that's exactly what's really happening is that here H1 is this guy, and the this 5 is this guy, and in the middle you have this the descendant is coming here, and this is just a denominator is just normalization. And on the other channel is determined by the 3-point function of the what did I write? 3-point function of the descendant. 3-point function of descendant. That's what's really happening here. Okay. And in particular, I think it's better to write down maybe. Yeah, so this one, in fact, is equal to as follows: sum of the x to the HP minus H3 and proper normalization, a normalization factor, which I'm going to omit, and then G inverse lambda prime, and then here we have the HP L lambda prime acts on phi 3 x and then H4 by appropriate normalization. So this is the case. So what's really happening is that this guy is equal to this part. And it's this part. It's this. And then, so this part is called inverse of Katz's Shapov matrix. So this is literally what's really happening. The problem here is literally here. So this part is just a phi 1 H1 or whatever H1, and then phi 2 of 1, and then a descendant, right? L is lambda HP L, and here you have the another piece. Lambda prime, and then phi 3x. Yeah, I think I made a mistake. This is y is okay. This is y is okay. Sorry. So this is just number. It's independent of x. So this is just number. So this is independent of x. So like this way. So here you have y here, this leg, and then H4. So this from this part you get this piece, and from this part you get this piece, and you group them together by inverse of Katz's Shapov matrix, like this. That's the rough form of conformal. And the power of x is just appear very simply. H to the x to the x is a cross ratio of Z1, Z2, Z3, Z4, and then HP, H3, and the power is just a linear combination of the conformal dimension, and then here the number of boxes will show up. Number of boxes will show up. So that's exactly the case. I will derive this one next time because I don't have the time. I only have 5 minutes left. So this is the next goal to derive everything. And yeah, unfortunately I don't. And this one can be computed by even like by just simply by representation theory of rational algebra. I think here I should write down HP. So Kac-Shapov is like this one, HP, and then L lambda prime, lambda, and then L minus lambda prime, HP. So this is the Kac-Shapov matrix. And lambda, the number box of lambda should be equal to lambda prime. So this is the Kac determinant. To get the Kac determinant, we already studied. And we just simply insert inverse of this matrix and glue them together. So that's a conformal block of the. And to compute the correlation function or 4-point function is just simply insert structure constant between 1 to p and 3 for p, and then just insert this conformal block. Somehow my notation is too long. I don't know why. Too long. Anyway. Okay, so that's the case, and yeah. And you can compute this one one by one, or even using Mathematica and so on. So maybe I don't think I have a time to explain each derivation, but I can just write down some results. But for the case of it's really some rational function of the conformal dimension. So there's f 2, 1, 3, 4, p, and x is given by 1 plus x and hp plus h2 minus h1. The level 1 is very beautiful and straightforward. And then 2hp like this. And the x curve term. So here, so lambda is really coming from this. The power here is really the like a level descendant you consider in the middle of this middle channel like this. So in the case of the level 1, it's just single box. So L1 and L minus 1 appear. And in the case of level 2, much more complicated. I'm not gonna write down. So it's just a function of h function, like h2 minus h1 and divided by 4hp and then 2hp plus 1 and plus 2 times the blah square. It's just a function, some rational function of h. Rational function is just a polynomial in numerator and polynomial in denominator, and then some linear combination. That is called rational function. That's how you get, and you can just determine this conformal block by using the representation rational algebra. So, and then the important thing is that this conformal block only depends algebra. Virasoro algebra. Virasoro algebra. And then this 3-point function, this one depends on the 2D CFT you consider. So this structure constant depends on which primary field you pick and which 2D theory you consider. Okay, which 2D theory you consider? For instance, if you consider the minimum model like a p equal to p equal to 3 and p equal to 4, this part will change. This part will change. C will change, but this part is independent. Of course, it depends on the conformal weight and so on. It will be different, but the way you derive is just simply the Virasoro algebra. Okay, so I think I will stop today here, and then next time I will derive how to obtain this result from this one. So that's I will do that next time. Okay, let's stop here.